In the next 3 lessons, we're going to look at electromagnetic induction. First of all, we're going to keep things simple by looking at the electromagnetic induction in a single conducting cable. Then we're going to extend that to the electromagnetic induction in a loop, and then into a coil or solenoid, and then we're going to look at a practical device which acts as an AC generator. Okay, so first of all, let's just look at the simplest form of electromagnetic induction, number 1. And what we've got here is a single, simple conducting wire. And it's made of copper or aluminium or whatever, but because it's a conductor, it contains free electrons. Okay, so you remember that from electricity, these free electrons are free to move through the structure of the conductor, and it is the electrons which carry the electricity. And so what we're going to do is we're going to just focus on just one of those free electrons in this conducting wire. Okay, let's say this one here. So we're going to focus on what happens to that single free electron to start off with. Now then, in electromagnetic induction, what we do is we move the conductor through a magnetic field. Okay, so we're moving it this way. And as that electron passes through that magnetic field, a force will be exerted on it. Okay, so we're moving the cable this way. The electron, as you know, has a negative charge, and a negative charge moving in this direction constitutes a conventional current moving in the opposite direction. So whenever a charge moves, that always constitutes an electric current. Okay, an electric current is charges moving, right? So when that is a negative charge moving in this direction, then actually the conventional current direction will be in the opposite direction. You remember when we looked at electric circuits that the flow of electrons or negative charges in an electric circuit is actually in the opposite direction to the conventional current. So what we want to note carefully is the conventional current direction as that negative charge, as that electron moves through this magnetic field. And the conventional current direction will therefore be this way. So what we want to do now is we want to think about what will happen to that negative charge, that electron, as it moves through this field. And to do that, we're going to apply what is called the left-hand rule, which you've already seen in this unit. And if you've forgotten about that, maybe you should go back and have a look at the lesson on the left-hand rule. Okay, so this left-hand rule helps us decide in which direction the force will act on the electron as it moves through the field. Okay, so what we notice first of all is that the magnetic field, which always goes from north to south, is downwards. So let's write that, magnetic field. And the magnetic field is your first finger. So we'll write FF there for your first finger. While the conventional current moves in this way, okay, that's your second finger. So we'll write SC for the second finger. And now then, what you've got to do is sort of orientate your left hand so that your first finger is pointing downwards, your second finger is pointing in this direction, and you'll notice now that your thumb is pointing in this direction, and the thumb represents the direction of the force acting on this electron, which is the direction of motion of the electron. Okay, so that's the thumb there, that's T for thumb. And so we notice now then that when our magnetic field is acting that way, our current acting that way, that's to say our electron is moving in that direction, then the force acting on the electron will push it towards this end of the cable. As a result, a force will act on not just that electron, but on all of the electrons that are passing through this magnetic field, and it will tend to push them in this direction. So what you're going to get is you're going to get an accumulation of negative charge at this end of the cable, and as a result, at the other end of the cable, you will get an accumulation of positive charges. Okay, so because you've got a negative charge building up at this end and a positive charge building up at this end, what you've just done is you've generated an electrical potential difference across this cable. Now then, this is what happens if the cable moves this way through the magnetic field. Now if I reverse the direction, then what will happen is that the current direction will switch around. Now the electron is moving in this direction and the conventional current direction will be in the opposite way, and as a result the force acting on the electrons will act in the opposite way, and the negative charge will then accumulate at this end and the positive charge will accumulate at the other end, and so the sign of the electrical potential difference generated across this cable will change. So let's just make a bit of space a minute. What exactly does the size of this electrical potential difference depend on? Alright, so it depends on two factors. First of all, it depends upon the speed of the conductor as it passes through or cuts through this magnetic field. Okay, so we can say that the greater the speed of the conductor, then the greater the electrical potential difference generated. And secondly, it depends upon the strength of the magnetic field. So the stronger this magnetic field, then the greater the electrical potential difference generated. Okay, now you've probably realized that actually this setup here isn't really particularly useful, because what we're doing is we're generating an electrical potential difference, but that's not really useful, because what we really need, if we're going to devise something which is useful, is to be able to generate a current. And you can't generate a current in a single connecting wire. We've got to have a closed circuit in order to generate a current. Okay, so in the next lesson we're going to extend this to look at what happens when we use a conducting loop rather than a single straight conducting wire. Okay, so that's going to provide us with something which is a bit more useful, and then we'll have a look at what happens when we extend that single loop into a solenoid.